Okay, so I'm going to try to record the free response question 1 for magnetostatics. Okay, so it looks like we have a magnetic field coming out of the page. We have a region right here. We're going to shoot an electron through, and the magnetic field has a strength of 0.5 Tesla, and they give us the mass of the electron. All right, and they want to know a couple of things. So let's see. They want to know, they tell us the strength of the field. They want to give us how far it is between the plates, and they say that there is, the plates are charged in parallel. The field magnitude is 400 newtons per coulomb. So I'm going to go ahead, because it's going to be cramped writing space, and I'm going to say, well, that electric field, E, is equal to V over D. So that's going to be 400 newtons per coulomb is equal to, man, that's a mess. Let's see, we can do some better things there. My apologies. All right. There we go. So if I'm looking for the voltage, it's going to be E times D. So it's going to be 400 newtons per coulomb times 0.20 meters, which, if I know how to multiply, V is going to be 80 volts, or 80 joules per coulomb, same thing. All right. So it says, label each plate as positively or negatively charged and indicate the direction of the electric field. So we got our voltage. Well, let's go back up there and look at that diagram. When we look at that diagram, it makes a lot of sense to me. If this is an electron, which it is, and it's negatively charged, which it is, then that negatively charged object is attracted in this direction. So this must be a positively charged plate here, and a negatively charged plate here. And then they want us to draw the electric field, so we know electric fields go away from positives and toward negatives. So my lines are not going to be very straight, but you can get an idea of what the electric field looks like. So there's my electric field. All right, so that wasn't too hard. Okay, let's go on down and see what they want us to do. Well, if I mouse over here, we can pull it up. We did part A. Part B says determine the electron's speed as it passes through the hole in plate 2. Okay, well, that's no big deal either. We know that as it goes through that electric field, that work gets done on it. The work done on it is equal to the voltage times the charge. So that's the 80 that we got just a minute ago, 80 volts or 80 joules per coulomb, multiplied by 1.6 times 10 to the negative 19th. coulombs, because that's the charge on the electron. So 80 times 1.6, well, let me think about that. That's, I think, 128 times 10 to the minus 19th joules. So that's the work done. That's also the change in kinetic energy of the electron. So delta KE is equal to 1/2 mvf squared minus 1/2 mvi squared. That's 0. So I have 1.28 times 10 to the minus 17th joules is equal to 1/2. The mass is 9.11 times 10 to the minus 31st kilograms. V squared, or VF squared, I should say. So I'm going to pause and get the calculator and figure out what that speed is, and then I'll come back and we'll finish this up. So the calculator gave me a value of 5.3 times 10 to the 6th meters per second for the final speed. So that should be fine. All right, let's go on to part C. Here's part C. It says on the sketch on the figure above, sketch the subsequent path of the electron in the magnetic field. Well, I'm not going to roll up to the sketch above. I'm going to do it right here. So what I know is here's the little gap, the electron's going to move through, and the field is coming out of the page. So if I use my right-hand rule, I can figure out the direction of the force, and that will help me find the direction that the electron is moving. Now, I'm going to use my left hand because it's a negative charge, so I'm going to point my palm out of the page because that's the direction of the field. My index finger is going to point to the right because that's the direction of the motion. So if I do that, my force is in that direction. So my particle is going to move in a circle like that. No big deal. Use the right-hand rule. Now they want to find the radius of the path of the electron. Well, if it moves in a circle, we know it experiences centripetal force. And the centripetal force, now I got to think about that, is equal to E times Q would give me F. Alright, but I also know that the magnetic force, which is what I want to use because it's in the magnetic field, is equal to BQV. The magnetic force is going to supply the centripetal force, so I'm going to set them equal to each other. MV squared over R is equal to BQV. And we used this equation in class. And when we did, we wound up with MV over BQ is equal to R. Well, we know our mass is 9.11 times 10 to the negative 31st kilograms. Our Q is, our velocity is, I think we said 5.3 times 10 to the 6 is what we found just a minute ago. Over B they gave us was 0.5 Teslas, and I couldn't find that at first, but it was to the left of that very first picture. So 1.6 times 10 to the negative 19th coulombs is the charge, so that'll get us the radius. And I'm going to pause and find a calculator and figure that out. Okay, so that's 6 times 10 to the minus 5 meters is the radius. At least that's what all that math is supposed to come out to be. Alright, and then I'm going to mouse up and do part E. Part E says determine the magnitude and direction of an electric field that would cause the electron to continue to move in a circle. I'm sorry, to continue to move in a straight line while in the magnetic field. Okay, so that's no big deal. We got that. So what we know is that if we want it to go in the straight line, the magnetic force is that way. We need to have an electric field in that direction, or an electric force in that direction, I should say. So they want us to draw and determine the magnitude and direction. Well, that's not the field. That's what I have drawn as the force. So we're going to come back in a minute and get the field. That's no big deal. All right, so I want my electric force to be balanced by my magnetic force. I said one thing and wrote another, but that's okay. The magnetic force is BQV. The electric force is E times Q. So the electric field is going to be B, which is 0.5 Tesla, times that speed of 5.3, I think it was 10 to the 6th meters per second. So half of 5.3 is about 2.65 times 10 to the 6th. And that should be newtons per coulomb for E. Alright, now let's check the direction out. Well, if the force is this way and it's a negative charge, it should make sense to you that there must be an electric field down here somewhere that is positive, because the electron is attracted to the positive region. And then we'd need a negative region here, so it would be repelled by the negative region. Electric fields go away from positives and toward negatives. So our electric field would need to point in a direction toward the top of the page, or I could say a direction opposite the force. That would work as well. Now I'm going to pause for a minute and go back and make sure my math is okay. I checked my math. It all looks great. So that's the only free response on this one. So I'm going to save it and put it on YouTube, and then I'll go to the next one.